So before the break, okay, we talked about acceleration. We talked about kind of just a review of what it is. Okay, that was just a review from Science 10. And we went through a few example problems using our first acceleration formula. And that's the one that we learned in Science 10, this one, that acceleration is any change in velocity. Acceleration is also any change in speed. Now this might seem a little bit weird. How do I get a vector quantity if I'm using all scalar quantities? Okay. The answer is it can be still positive or negative, even if I use speed. If the speed is decreasing, the acceleration is negative. Right? If the speed is increasing, the acceleration is positive. If I'm dealing with vector quantities, like this is velocity, and I'm looking at like 30 degrees north of west, then my acceleration will be 30 degrees north of west. Right? But if I'm dealing with scalar quantities, any change in velocity can still be vector. It's just positive or negative. Right? So if that comes up, and it says an object changes its speed from this to this, your acceleration still needs a positive or a negative quantity. Okay, does everyone follow there? Acceleration is always vector. Okay, so today we're going to look at using the rest of these formulas because we didn't get to any of these. We did talk about how these two formulas come from your velocity versus time graphs. Right? If I had a velocity versus time graph that looked like this, okay, basically what these two formulas are doing are calculating the area under the line. Okay, this first one, VI times T, calculates the area of the rectangle because B would be VI and T would be X, the base times the height. And then this triangle here is calculated by the 1/2 AT squared. This formula calculates the whole box and then subtracts this triangle. And still calculates exactly the same thing. Okay? The area between the line and the x-axis. All right? So what we're going to look at today is using these other formulas. Now, I don't know if anybody realized this when they started looking at these formulas, but these two formulas have t in two places. And one of them is squared and the other is not. Anyone else intimidated by that? Well, good on you, because you're better at math than I am. Because in order to solve for t, using either one of those, if t is not if vi is not 0, would involve the f word, factoring. You thought I was going somewhere else with that. Shame on you. Okay, so I would have to factor either one of these if I was going to solve for t if vi or vf were not 0. If vi or vf are 0, how does that change that I don't have to factor to solve for t?
Because t times 0 is just 0.
Right. Okay. If vi is 0 and I multiply it by t, it doesn't matter what t is. This is gone. This is 0. 0 plus whatever. I don't have to worry about it now. There's only one t there. Okay. And it's the same with the other formula. So you may be asked to calculate t with these two formulas, but only in a situation where vi and vf are 0. Because we can't guarantee you've taken Math 20 yet when you take physics. Okay? Because you may take physics 21st semester, you have math second semester, whatever. You're taking concurrently and you haven't learned to factor yet. So, lucky you. You don't have to factor. All right, let's have a look at, we already did that one, and we did those ones. I want you to write this one down, and then we'll walk through it together. So I'll give you a minute to get it written down. So when we first started talking about acceleration, we said that the most important part of solving an acceleration problem is writing down the givens. Having the givens allows us to choose which formula is most appropriate for that problem. Basically, it's a matter of matching up what you have with which formula has those things in it. Right? So for this question, we have a cattle train traveling west at 16 meters per second. What did they give me? That's my initial velocity, right? That's VI. 16.0 meters per second west. All right, and it's brought to rest. What did they give me there? final velocity. And what is it? 0. Okay, in 8 seconds. Okay, find the displacement of the cattle train. So they want me to find D. Assume uniform acceleration. Now, I don't know if anybody remembers this, but I said anytime you use this one particular formula, this has to be true. Okay? The acceleration has to be uniform in order to use this formula. Now, if I'm looking at my givens here, I don't even have acceleration. It's not one of my givens. This is clearly an accelerating object, but I don't have it. And it wants me to find D. What's the only formula I can use here? Which of these formulas calculates D, doesn't have acceleration, and has the two V's in it? The bottom one, this one. Okay? Remember I said that using that formula, okay, it's kind of, we don't use it very much because really all it is this. D equals average velocity times time. It's really V equals D over T, which we don't like using for acceleration because it assumes a constant velocity. But in this case, it's taking into account that the velocity is changing by saying VF plus VI divided by 2 will give me the average. If it's uniform, the average will be right between the two. And we know that because on a velocity versus time graph, that's what we use to calculate displacement. Right? We assume that this VI plus VF divided by 2 gives me the average. It gives me the base times height over 2. Okay, so it's basically the same thing as what we're doing here. Is everyone okay with that? All right. All right, but we have to have uniform acceleration. If this graph looked like this, that's no longer uniform. There's two different accelerations there. This formula doesn't work. Okay? All right, so now I've got my formula. I've got to use, put it back in the right one. Okay, there we go. Okay, so I'm going to be using this formula, and I'm solving for D. So that's great because I don't have to manipulate it. Okay? I just have to plug my numbers in and solve. So D will equal 0 plus 16 over 2 times 8 seconds. 16 over 2 is 8 times 8 is 64 meters west. Okay, everybody all right with what I did there? Okay, let's look at manipulations of this formula. If I wanted to solve for t, what do I do here? It's actually a really easy manipulation, but we can't get to it because we look at this formula and it like stumps us. We see all this stuff in brackets and we're like, oh God, what do I do? I must have to move t, but I don't.
You divide the whole VF plus VI over 2 on both sides.
Exactly. If it's in brackets, do I have to do it first? According to order of operations? So that means it's just a number, one single number that I'm multiplying by t. Remember, we just finished saying this formula really means this. If I wrote that and asked you solve for t right away, you'd say divide by v. Right? Well, that's all we're doing here. I'm dividing by the average velocity. I'm going to take this whole mess over to the other side all together. Because if I was doing this calculation, this is just one number. I'd figure out what it is first because it's in brackets. Okay, I'd follow the order of operations and I would do it first. So what I would have is that t equals d divided by vf plus vi over 2. Okay, that'll calculate t. All right, what if I wanted to calculate either one of the v's? one side, view the other. And move what's not attached first. What's not attached to either one of those V's? T, yeah. And if I get rid of T, do I need the brackets anymore? Nope. All right, so I'm going to divide both sides by T. All right, this should make sense. Average velocity is total displacement divided by total time. Okay, so now the brackets are gone. I effectively don't need them anymore. I want to solve for, doesn't matter either one. What do I do with the 2? Multiply both sides by it. So just bring it over there, put it on the top. Okay, and then what do I do with the one I don't want to solve for? Subtract it over to the other side. Okay, so I'm going to have 2d over t minus either VF or VI, whichever one you're not solving for. Okay, so that would equal VI. And the other way around, if you were solving for VF. Okay, everybody all right with that? Just that bracket throws everybody. When you see that bracket, like, oh, brackets mean I can't do anything. No, they don't. Okay, brackets just mean you got to do things in a certain order. Okay, try those two. They both involve that formula. All right, so for number 1, okay, it says we got a hound running at a velocity of 16 meters per second south. So that's our VI, 16 meters per second south. And that's velocity. Okay, slows down uniformly, keyword, okay, to a velocity of 4 meters per second south. Okay, what's the displacement of the hound during this time? So that happens in 4 seconds, okay, and we're looking for D. All right, so the only formula I can use is the one we just used. D equals VF plus VI over 2 times T. I don't need to manipulate, just plug in my numbers. So I'm going to have 4 plus 16 over 2. Okay, so that'll be 20 over 2, okay, times 4 seconds. So 20 over 2 times 4 should be 8. No, 20 over, that's 10 times 4 is 40, right? So we got 40 meters south. Okay, is our total displacement. Everybody all right with that? Okay, how are we doing on number 2? Need to go over that one too? Yeah. All right, now, number 2, we have a direction change. That's the key thing to watch for here. First part of this, up the hill. Second part of this, down the hill. How do I represent those mathematically? Positive and negative. All right, so ball moves up the hill with an initial velocity of 3 meters per second. As soon as I see that, I go positive equals up. So I remember for when I get to the end. Okay, so VI is 3.0 meters per second, and it's positive. Okay, 4 seconds later. This is terrible. This is the worst thing a physics book can do. How many significant digits does FOUR have? I have no idea. Nobody writes numbers as words in physics. That's awful. So it's 4.000000. I don't know. It can't affect our significant digits. It's essentially a counted number. Okay? And counted numbers have absolute certainty. If I count the number of people in this room, I'm absolutely certain that's how many people there are. There's no arms or legs on the floor. Okay? There's no 0.5 of a person in here. Okay? That's how many people there are. Counted numbers are 100% certain. If they write it like that, it's a counted number. Okay, so VF is negative, or sorry, that's time, time is 4. Okay, it's moving down the hill at 9 meters per second, so VF will be negative 9.0 meters per second. Find the displacement of the ball from its point of release. Okay, so D will equal then VF plus VI over 2 times T. So that'll be negative 9 plus 3 over 2 times 4 seconds. All right, so negative 9 plus 3 is negative 6. Negative 6 divided by 2 is negative 3 times 4, 12 meters downhill, because it mathematically comes out to negative 12, and I wrote positive equals up. Their answer? Wrong. Why? What did the question give as a vector? Up a hill, down the hill. My answer has to have that vector. That's the vector given in the question, that's the vector my answer has. I can't just go negative. Negative could mean south. It could mean west. It could mean anything that I apply negative to in a question. Negative is not specific enough if you're given actual vectors. Okay? Now, is down the same as downhill? It is not. That's something people make a mistake on all the time as well. Down is straight down. You cannot go down a hill. You can go down a hill, but you can't go down, okay? Like, so people will write this and they'll go 12 meters down. So you fell through the hill? Because that's the only way you went 12 meters down, okay, is if you like drilled a hole and fell in it. Okay, that's the only way you go down. Okay. Write this one down. And then we're gonna go through it. Okay, so this is kind of an example of what I was talking about before, where we might be given a scalar quantity along with vector quantities and ask to calculate a vector quantity from that, okay? And that's what's going on here, okay? A golf ball initially traveling at 25 meters per second. No vector. Okay, then they tell me the acceleration is negative. So all I know is the acceleration is in the opposite direction of the golf ball's current velocity. Would you agree? Okay, so I'm going to write that that is actually positive, that 25. Okay? Because when I calculate displacement, does displacement need a vector? And even though this ball is accelerating negatively, it's still moving positively, right? It's no different than if I, slide something along the floor. It eventually stops. It moves forwards, but it accelerates backwards. Okay? Friction won't make something move backwards, but it can make it accelerate backwards. It can slow it down. Okay? That's why, thankfully, using your brakes in your car never actually causes you to go backwards, even though it makes a negative acceleration anytime you apply them. It'd be really inconvenient if your brakes actually made you go backwards. Okay? Stopping at stoplights would be a really different experience. So, we've got the golf ball initially traveling at 25 meters per second. I'm going to write that that's positive because they tell me the acceleration is negative. Okay, find its displacement after 2 seconds. All right, what formula am I going to use? I've got VI, A, and T, and I'm looking for D. The first one, right? This one. D equals VI times T plus 1/2 AT squared. That's the formula I've got to use. It's got all the things in it that I have and the thing I'm looking for, right? And I should indicate that this is a vector quantity and that is a vector quantity. The V wasn't, okay? And that's all right. So now, I don't have to manipulate it. I just need to solve. So VI was 25, positive 25, times 2 seconds, plus 1/2 times negative 20. There's the mistake people would make in this question. They forget to put the negative on it. This thing goes a lot further if you don't make that acceleration negative, because you're telling it by hitting the sand trap, the ball sped up, and it would definitely go further, whichever is appropriate. I don't teach English. Okay, times t squared, 2 squared. All right, so we got 50 times negative 10 times plus 40, 90 meters? I shouldn't do that in my head, that's a terrible idea. Okay, so we've got 25 times 2 plus 0.5 times negative 20 times 4, 2 squared. Okay, see, I said 90 because I didn't make the 20 negative in my head. See, what's the danger of doing it in my head? Okay, 10 meters. So it travels 10 meters forwards. Okay? Or in this case, I could probably just say positive 10 meters. Okay? They didn't give me anything other than that, but I mean, this is a real world example. The ball was moving forwards when it hit the sand trap. Okay? Someone didn't hit it backwards. You get big trouble for hitting the ball backwards on a golf course. All right. Questions on that one? All right, let's look at manipulations of that formula. Okay, if I wanted to solve for VI, what do I move first? Even before T. What's not attached to VI? The rest of it, yeah, this whole thing. Okay, I can subtract this whole thing over here because according to order of operations, I would have multiplied all these things together before adding it to this. So I can move this whole thing over. It's just one number. Okay, it's made of two numbers, but it's just one number. Okay, so I'm going to have D minus 1/2 AT squared equals VI times T. Now what do I do? Trying to get VI by itself.
Divide T.
Right, divide both sides by T. Okay, does that make the squared cancel? It doesn't. If all of these things on the top were being multiplied, it would. But because there's a subtraction or addition operation here, that doesn't happen. Okay, because I would do the top before I did the bottom. Okay, so it won't cancel in that situation. Okay, so now I've got it manipulated, I could plug in and solve. All right, so that's one of the manipulations of that formula. What if I wanted to solve for A?
It would subtract VI times T.
Right, subtract the VI times T. Now what? All three things are being multiplied together, so if I want to move anything, I have to just divide. Okay, just taking over the other two things, they go together. Okay, now I'm solving for A. This is going to make you flex your algebra muscles a little more, okay, than what you're used to before. Okay, everybody all right with that? Okay, now we were talking earlier about T being in two places. So you wouldn't have to solve for it unless VI was 0. So if VI is 0, this is 0, which effectively eliminates the plus sign even. Okay, 0 plus anything is whatever you added to it. So all of this is gone, and I want to solve for T. What do I do? Same thing I did before. All three of these are being multiplied together, so to move the half and the A, I would divide. Okay, that solves for T squared. What do I want? I want the square root of T squared. T. All right, that's it. That's all the manipulations you would have to do with that one. Okay. Now, please don't write all those down on your formula sheet. Okay? Because if all you're doing is writing down all the manipulations I do here, you'll never learn how to do it for yourself. And I'm a big fan of the whole, give a man a fish, you feed him for a day, teach him to fish, they'll feed themselves for life. I'm a big fan of that idea, okay? If you just write these down, and you're taking a fish for a day, okay? But as soon as I take these away on the test, you starve. So I don't want that for you. I want you to learn how to manipulate them yourself, okay? So make sure you're doing that manipulation yourself, right? All right, try those two. They both involve that formula. And neither one asks for time, so yeah, you're good there. So on number one, we've got this skier moving down a uniform slope at 3 meters per second. So VI is 3.0 meters per second down slope. Okay, the acceleration down the slope or down the hill is 4 meters per second squared. Again, down slope. Important to know that those two are in the same direction. Okay, find the skier's displacement after 5 seconds. All right, so just a matter of plugging in directly. We don't have to manipulate for that one. VI times t plus 1/2 AT squared is the only formula that has all that in it. Okay, so we would have 3 times 5 plus 1/2 times 4 times 5 squared. Okay, and so we should get 65 meters downhill. And this time they have the right vector on their answer. Actually they don't, because they say down, which we said is not the same as downhill. These people are accelerating through the hill, not down the hill. Okay? Down is vertical, down the hill is angled. All right, how many people are still working on number 2? Okay, I'll give you a few more minutes on number 2 then. All right, so on number 2, we have a motorcycle traveling at 100 kilometers per hour. Uh-oh. What do I have to do with that? I got to convert it to meters per second. I have an acceleration that's in meters per second squared, and for God knows why they gave me the time in minutes. Okay, so this question is just all about making you do a bunch of unit conversions. Okay, so for VI, we got to divide the 100 by 3.6 and it comes out to 27.7 repeating. Is that right? Okay. Meters per second on a flat road. Okay, and it applies the brakes. All right, that's a trick here. It applies the brakes at 0.8 meters per second squared. What do I have to remember about that 0.8? Because it's being supplied by brakes. Which way is it? Backwards. It's slowing down. Okay, applying the brakes makes a negative acceleration. See, I was foreshadowing. I think that's the right word. Okay, before when I was talking about how it's really important to make sure you got slow down, speed up. Okay, so the acceleration is negative 0.8 meters per second squared, right? Because we're slowing down, and it's going to do that for 1 minute. Okay, how far does the motorcycle travel? So again, we don't have to manipulate here. Okay, we're lucky. And it actually says how far, so it doesn't even matter which direction. The only thing that's vector here is the acceleration. Everything else is scalar, and that's okay. Okay, how far is distance? So D equals VI times T plus 1/2 AT squared. Plugging in the numbers, that's going to be 27.7 times 60 plus 1/2 times negative 0.8 times 60 squared. Okay, so if we punch all that in, so 100 divided by 3.6, so we get all of them. Okay, so that times 60 plus 0.5 times negative 0.8 times 60 squared. All right, 226.6 repeating, so that's going to round to 2 significant digits to be 2.3 times 10 to the 2 meters. No vector on that, because it's how far, which is distance. Okay, so are there sometimes tricks in the context of a question? And that's a prime example of it. Okay, that's one of those things where the question is checking to see if you understand that by applying the brakes, you are accelerating backwards. Okay, and understanding that in that case, acceleration needs to be negative. Right. Any questions on those two? So you're lucky you didn't have to manipulate either.
I'm not quite sure where I went wrong with my calculation, but I ended up getting 2.2 times 10 to the 3.
Okay, did you round this off?
No, I did not.
Do you have it in same way I do? 27.7 repeating, like I used the answer?
Yeah, I just didn't put it all in one. I did it through multiple steps.
Okay. Did you, when you got 2.2? So somewhere along the way, your decimals got rounded off. That's the only way you'd arrive at 2.2 times 10 to the 2. If there's somewhere your decimals got rounded off. Right, there's no other numbers that would cause you to have that. All right, I want you guys to write this one down, okay, and then we're going to go through it. All right, let's have a look at this one. So, a speedboat slows down. Keyword, my acceleration is negative. Okay, and comes to a stop. What did they tell me there? VF is 0. Okay, process takes 15 seconds. Now, find the displacement of the boat. All right, what formula am I going to use here? Second one. D equals VF times T minus 1/2 AT squared. Okay, so on this one I'm looking for the displacement of the boat. VF is 0, so what's VF times T? Right, but in this case, that negative has to stay. Before, when we used the other formula, it was a positive, we could just forget about it. Okay, but in this case, the negative has to stay. So if I'm looking for the displacement of the boat, okay, now I'm going to go essentially 0 minus, okay, this, or I just leave the negative in there, 1/2 times negative 5 times 15 squared. This is why that negative is important, or that minus is important, okay? This number here is also negative. So when I subtract the negative, I get a positive. Even though this thing is slowing down, it's still moving forwards. Okay? And that's why that negative has to stay, to make sure we get the right vector on it. All right, so we're going to have the, we can just do it like this, negative 0.5 times negative 5 times 15 squared. Okay, we'll get 562.5. We could also do this, 0 minus 0.5 times negative 5 times 15 squared. Either way, we get the same answer, but we have to keep the negative in there in order to get the right vector. We get positive 562.5 here, no matter what we do. All right, so we're looking at 5.6 times 10 to the 2 meters as our final answer there. Okay? Everybody all right with that? This had better have been a long lake, because that's half a kilometer to stop. It's a long lake. All right, any questions on that? Okay. Try these. Oh. Yeah, you can do that one because it's 0. Okay. Yep, try both of these. You can do them both. Okay, so on number 1, okay, we're talking about the arresting device on an aircraft carrier. I don't know if anyone's ever seen what it looks like when a plane lands on an aircraft carrier, but there are these arresting cables that go across the deck, okay? And there's a hook on the back of the aircraft. So when the aircraft lands on the carrier deck, it is a violent stop, okay? The plane hits the carrier deck, its nose and front wheel still in the air. It hits the arresting cable, which promptly slams the nose down and yanks the plane to a stop. Okay? They're not kidding when they say that's negative 15 meters per second squared. It's almost 2 Gs. The force a fighter pilot feels when stopping is that he's being thrown forwards by a force almost twice that of gravity. Okay? That's like the worst whiplash you could imagine. Okay? But it is violent. So these, if you ever look at a fighter pilot, they have huge neck muscles. Okay? Because not only do they have to endure all these G-forces and hold their head up straight and all that, they got to do it with a heavy helmet on. Okay? They all wear a big helmet when they're flying, and it's heavy too. Okay? So they get the really big neck muscles. Okay? So this arresting device is going to stop the plane. So they told me that VF is 0 because it said it's going to stop it. and it's going to do that in 150 meters, which is not right. It's actually way less than that. Okay. And it's going to do that with an acceleration of negative 15 meters per second squared. Okay, find the time it takes the plane to stop. Okay, so the only formula I can use is the one we just looked at. D equals VFT minus 1/2 AT squared. Since VF is 0, that's all gone. And now I can solve for T. But I have to remember to take this negative with me. Okay, so I'm going to solve for T by dividing both sides by negative 1/2 of A. Okay, and then what do I have to do with that? Because that solves for T squared. Square root. Okay, so now I've got my numbers here. So it's going to be the square root of, what was our distance there? 150 meters it said. Okay, divided by negative 1/2 times negative 15 meters. And again, these two negatives make sure that I get a positive number. If I forget that, don't worry. Your calculator will tell you you did something wrong. Because if you try to take the square root of a negative number, your calculator has a conniption fit, okay? And it won't do it. So when I plug all these numbers in, I'm going to have the square root of 150 divided by, and then you have to put this in brackets, okay? Negative 0.5 times negative 15. Okay, so we're getting 4.5 seconds as our answer there. Okay, everybody all right with that? All right, that's the toughest manipulation of that formula, okay, for sure. All right, I'll give you a few more minutes on the 1968 Corvette. Okay, 1968 Corvette came with 2 engines, incidentally. One of them, 300 horsepower, 327 V8. That's not the one that did that. Okay, that's the 427. 427 cubic inches of Detroit muscle. Okay, that could propel that car to 100 miles an hour in 6.2 seconds. Most production vehicles today can only go to 100 kilometers per hour in that amount of time. Okay, so this thing was a speed machine, man. And that was back in the 60s when, well, nobody cared about what kind of gas mileage you got. Okay, you might be able to, it's kind of like the Bugatti. You guys know what I mean? The Bugatti? It's the fastest production car. It can go like 267 miles an hour, but it can't go 267 miles in 1 hour because it runs out of gas after 20 minutes. Yeah. Okay. So nobody cared. At that time, gas cost like 3 cents a liter. Yeah, wouldn't that be nice? But it's more expensive now. Anyway, that aside, I'm a gearhead. That kind of stuff's cool. But the 1968 Corvette took 6.2 seconds to reach to accelerate to 160 kilometers per hour. Now I need that in meters per second, and that's the final velocity. Okay, so I got to divide that by 3.6. All right, so we're looking at 44.4 meters per second. Okay, and it could do that in 220 meters, which is probably like a quarter mile. Okay, D equals 220 meters. All right, so we need to find its acceleration. So we're still going to be using this formula, D equals VF times T minus 1/2 AT squared. Okay? No, we're not. Yes, we are. Sorry. VF's just not 0 here. Okay, so we know what VF is, okay? And we know what T is. So now we're solving for A. So what do I need to move before I can solve for A? It's a tricky manipulation here. This first. How do I get it to the other side? That's the tricky part. I have to subtract it. VF times T is positive. Okay? I'm not subtracting it. I'm subtracting this part, but I'm not subtracting the VFT, okay? It's being added, so to move it, I have to subtract, okay? So D minus VF times T equals negative 1/2 AT squared, right? This is where you really have to keep track of all the positives and negatives, right? I want to solve for A, so I'm going to bring the 1/2 and the T squared over to this side by dividing them, and I'm bringing the negative with it. Okay, so that's going to leave A on the other side. Now I can plug in my numbers. So 220 meters minus 44.4 times 6.2 seconds divided by negative 1/2 times our time, which was 6.2 seconds squared. Okay, so when I punch that into my calculator, it's a little bit messy. 220, okay, minus 44 point. Actually, I should use the whole number here. That's bad. Okay, so that's the top. Divide that by the bottom, okay, and that's going to be negative 0.5, and that has to be in brackets. Times 6.2 squared. Okay, so I'm getting 2.9 meters per second squared as my acceleration. And it's going to be positive because it's forwards. Okay, everybody all right with that? Bit of a tricky manipulation, bit tricky to punch it into the calculator correctly. Just remember, anytime you're doing any of these acceleration formulas and you've got operations, multiple operations, top and bottom, know it's always top divided by bottom. So top in brackets, bottom in brackets. Okay? If you don't put them in brackets, your calculator does them from left to right. Okay? It obeys the rules of order of operations, and in this case, you don't want that. Okay? All right, questions on that formula? Okay, we got one more we haven't talked about yet. So, try this one. All right, so on this one, we have a bullet that accelerates the length of the barrel of a gun, okay, that is 0.75 meters in length. So it's a rifle, okay, it's a long weapon, okay, so the D is 0.750 meters. And the acceleration is 5.35 times 10 to the 5 meters per second squared. Is that a lot? That acceleration is massive, and it should be. It's a small piece of lead being propelled by an explosion, right? I mean, the physics behind how any kind of firearm works is, okay, when the whole bullet, including the round, are in the chamber, okay, when the hammer strikes it, it causes an explosion. It detonates the gunpowder. Okay, that explosion separates, okay, the actual bullet from the back end, where the round, where all the gunpowder is. And because it's sealed tightly, the gases cannot escape anywhere but out the front end of the barrel. So they push the bullet all along the length of the barrel. So the longer the barrel, the greater the length of time and distance over which that force can be exerted, okay? And if you remember back to Science 10, work is force times distance. So the more distance that force of the explosion can work over, okay, the more energy the bullet will have, and thus the faster it will be going when it leaves the barrel of the gun, okay? So that's why pistols don't typically fire as far as rifles do. All right, so we've got that acceleration, okay, and we're looking for the speed it exits the barrel at. Now, they only gave us 3 pieces of information. They didn't tell us time, but there's one thing we can get from the context of this question. What is it?
Initial velocity.
The initial velocity. How fast is the bullet moving before I pull the trigger? 0. It's at rest, okay? It didn't say the person holding the gun was running. Okay, I mean, if that was the case, then VI would be something other than 0, right? But you generally don't run and fire at the same time. It's like running with knives and sharp objects. Okay, you just don't. Okay, so VI equals 0 meters per second. So we've got those three things and we're looking for VF. That means that we're going to be using our last formula. VF squared equals VI squared plus 2AD. Now, luckily for us, this formula is going to be really easy because VI is 0. Okay, so VI squared is also 0. So all I have to do is plug in my numbers. So VF will be the square root of 2 times 5.35 times 10 to the 5 times 0.750 meters. Okay, so that's 2 times A times D, square rooted because VF solves for VF squared. Okay, bullet leaves the barrel of the gun at 895.8 meters per second. I think we have 3 significant figures here, so 896 meters per second. Okay, here's a thought you can rock yourself to sleep with tonight. That's almost 2 times faster than sound. What does that mean for you if somebody shot at you? Yeah, there's a saying in the Army, you never hear the bullet. Okay? And you might hear the hiss of it traveling through the air, but you'll never hear the sound of it being fired because the bullet goes faster than the sound that produces it. Yeah, scary thought. Okay? Has anyone ever seen or read American Sniper? Okay. They actually do a pretty decent job of portraying that in the movie. Okay? About Chris Kyle. But the longest sniper shot is actually held by a Canadian sniper. And it's almost 4 kilometers. Don't get on that guy's bad side. Okay? You look out this window, you can barely see something 4 kilometers away. That person unfortunately aimed a rifle at something and hit it from that distance, and it was a person, unfortunately. Okay? So yeah, that's not somebody you want to be on their bad side. Okay, so that's fast. Okay? 896 meters per second. Okay, and a lot of rifles, especially high-powered ones, would be even faster than that. Yeah, fast. Scary. Don't get on that guy's bad side. 4 kilometers. Do you realize how long something is in the air when it travels 4 kilometers, even if it's traveling at 1,000 meters per second? It's in the air for 4 seconds. You know how far something can move that you shot at in 4 seconds? Okay. And the whole time a bullet is flying through the air, because this leads to our next concept. What is it also doing? It's falling. Remember, this is something that still is going to be acted on by gravity. In 4 seconds, an object can fall a long way. Okay? In the first second of flight, it'll fall 4.5 meters. In the first second. Right? It flies for 4 seconds, it's going to fall even further. Okay? So a person who shoots that shot has to aim way above their target to correct for how much it will fall. And that's not even taking into account that it might have been a windy day. And the wind could push the bullet left or right along its path as well. This is why snipers rarely work alone. They always have a spotter. That's a person who's telling them things like windage and drop and all of that kind of stuff, and relative motion. Okay? If they're shooting at a moving target, they have to correct not only for drop, windage, but also motion of the target, and they have to lead it. Right? So yeah, these are people who are incredibly well trained. Okay? Unfortunately, to kill people, but they're well trained. Okay? In order to be able to make shots like that. Okay. All right, try these ones. Let's not do number 1 though, because number 1 actually doesn't require us to use this formula, but number 2 does. So let's have you try number 2. Okay, remember to convert your kilometers per hour to meters per second. So for this last one, we're told that we're talking about on-ramps, okay, which if they're designed properly, work really, really well, right? Obviously in like Calgary, only some of them are designed properly and some of them don't make any sense at all, like that one at 162nd, okay, which was like oh, we're gonna design this whole brand new interchange system. And they replaced one set of stoplights with 4. Which makes no sense, but whatever, okay? Some exits, like basically everything on Stony, works really good, okay? They're designed with true on-ramps and off-ramps and very few stoplights. Putting stoplights at the top of an overpass kind of reduces the effectiveness of them because traffic can back up onto the highway. Okay? So we've got this case where we're having to increase in speed from 50 to 100. So we know that our initial velocity is 50 kilometers per hour, which is what, 13 point something? 13.8. 13.8 meters per second. On our final velocity, 27.7. Is that right? Yeah. Okay. Meters per second. And we've got to do that. We got to find the minimum length of the on-ramp. So this is what like an urban planner would do, okay, in designing an interchange. Okay, so we know their acceleration would be 3.8 meters per second squared, and that would be positive because they're accelerating, they're actually speeding up. Looking for D. VF squared equals VI squared plus 2AD. If I'm looking for D, first thing I do is subtract VI squared. So I'll have VF squared minus VI squared, and then I'll divide both sides by 2A, and that'll leave me with D. Okay, plug in my numbers. So we'll have our 27.7 squared minus our 13.8 squared divided by 2 times 3.8 meters per second squared, and we'll get our 76 meters. Okay, everybody good with that? Okay, remember, the purpose of an on-ramp is to accelerate. That's why they're sloped. So when you merge, accelerate. I don't know about you, but I get really annoyed by people who think the merging lane is for driving slow. It's not. To press the pedal on the right, car go fast. Okay? Do that. It's much safer to actually be going highway speed when you merge onto the highway. Okay? Safety tip for you. Rant over.